Good morning, everybody. My name is Ann McMahon, and I'm with the Office of Sponsored Research at UW-Bothell, and I'd like to welcome all of you today to our Husky Highlights. Our first speaker today is Dr. Caleb Trujillo. The title of his talk is Concept Models Reveal Changes in Students' Cognitive Structures for Biology and Statistics. Dr. Trujillo is an assistant professor in the School of Interdisciplinary Arts and Sciences. His research spans three broad areas related to visualization: teaching, number one, teaching science as it is practiced; number two, teaching different ways to think; and three, mapping the scholarship that informs teaching. And through these three areas of scholarship, Dr. Trujillo strives to enhance instruction and advance student achievement and retention in data-intensive fields to support the next generation of visualizers. In this talk, Dr. Trujillo will describe how he explores the changes in models as evidence of learning by using a network approach to analyze student-constructed models of biological systems and statistical concepts. So with that, I'll turn it over to Dr. Trujillo.
Great, yeah, thank you. I really appreciate the invitation to come share the work I've been doing. And that was a great introduction. This was a funded project. Thank you for the SRCP that made this possible. This has been an idea I've been kind of cooking up for years. And so it was great to have some initial funding to kind of start to seed the ideas and finally have some evidence to say, oh, this is where I'm at. So the way I like to think about my research is oftentimes addressing some of the big gaps that we have, and especially in these areas that are kind of between disciplines. So one area in particular is, we see this huge growth in the information sciences and data science, and a lot of different disciplines have really, capitalized on that. Healthcare, business. You see some of the biggest tech giants, they've really leveraged this data-intensive view of the world. And leading them to better decision making, and of course providing the services that they need to. But education has been a little slower to adopt, and so there have been many calls for why we need to try to bring in more of these kind of computational and data science approaches into education. In particular, we need to start focusing. Some of the calls said we need to start focusing on building bigger data sets to kind of start to see these larger patterns that are kind of underlying teaching and learning. We also have a lot of new learning technology that's being implemented, and especially after so many have gone into distance learning through constraints of the pandemic. And we also see there's this need to account for differences among learners that really have been ignored through the kind of standardized testing that became really popular over the last couple of decades. So with all of these calls, who is going to be the ones to kind of find that middle ground between these kind of data intensive fields and how we teach? And in particular, I'm interested in STEM education, and I think it's ripe for a re-examination, especially when it comes to the way that we assess students and how they learn about science, technology, engineering, math. So there are a couple examples of people bringing in these data science approaches into the classroom assessment level. And but most of these are focused on multiple choice and written responses. And they still have this kind of old school view that the way that we measure learning is on a linear scale. You can get anywhere from 0% to 100%. And when you give this test out to students, you get a distribution back. And it usually looks like some kind of skewed curve like this, where most people passed, but a few didn't. Now, what's interesting about this is, two students can have the exact same score, but have completely different understanding of the subject. And I think what's troubling is there's this underlying assumption that just having higher score means you have a deeper understanding in that particular subject. And so this has been pervasive in STEM education. Probably a lot of other fields see this too. But it goes against a lot of what has been happening in the background, and policymakers and advocates recommending that STEM education start to move away from these kind of fact-based and knowledge-based measures. My background's in biology, so you probably think about biology as just memorizing lists of terms, memorizing pictures of structures that you then, regurgitate on the test. So we're trying to get away from that, and we're trying to become more meaningful in the way that we assess what it means to be to reach achievement in science. So the assessment should reflect that. And one way that people have been advocating that we kind of change the assessments is start to bring in more scientific practice. So rather than simply giving students a list to choose what is the correct term, instead we want to engage them in things that are authentic, the same things that scientists would do. And in particular, I'm focused on how students use models and develop models in order to construct explanations. And so I've been studying this for a long time, but it gets a little tricky when you hit the assessment phase. And so one way I like to think about this is through a learning framework, right? And one way you can think about the way people learn is that they have what's called a mental model. And this is kind of the working memory of how they believe the world works. So the way to think about this is everybody has an internal representation, and that internal representation is a collection of ideas and concepts. And when you have those relations, it creates an organization. We call this a cognitive structure. And so somebody might have some initial ideas walking into the classroom, right? They might believe that the world is flat, but through learning, the idea is that as they take in new information, they're going to restructure their thinking, their mental models are going to change, and they're going to view the world in a different way. And what would be nice as education researchers, we just kind of crack that skull open, look inside, and see all these concepts moving around. But unfortunately, that's not how it works. So what we rely on in assessment and education research in general is what we call external representations. So when somebody is trying to explain what their ideas are, they're externalizing their internal models. And that can be in the form of speech, that can be in the form of writing, drawing, even bubbling those little circles on the test. That's an external representation. So what I'm interested in is how can we kind of create ways of measuring these structural changes that are happening inside somebody's head, and in order to make inferences about the effectiveness of our teaching and provide feedback to the instructor so that they can, do better, create better materials and help this transition. So big takeaway here is learning is not linear, and there is no final state of knowledge. I've never met somebody who said, yep, I'm completely done learning. I'm not learning anything more. And I think the real gap in STEM education is that our assessments should reflect this kind of assumption, right? So we need assessments that can show how people are restructuring their understanding and provide knowledge. And we also want to show that learning continues to grow, and everybody has unique understanding, both at the beginning of the course. They're not coming in with clean slates. They're coming in with their own set of experiences and ideas, these students. And that's really at the heart of constructivism. And so it aligns well with a lot of different learning theories that are common in education. So my motivation for working on this project actually came from my postdoc with Dr. Tammy Long at Michigan State. So she's been using what we call concept models in order to assess her students in biology. And there she teaches really huge lecture halls, like, almost 400 students. And she realized, like, she wanted students to write these essays, but it's taken way too long to grade everything. So instead she had her students construct models so she could see how they're relating ideas and create these kind of representations that are easy to share and understand where somebody is coming from, and also give feedback. Now, the motivation here is that there are these structured behavior function models. So what you see is like a student will have a concept and they'll be asked to relate this concept to another one through these arrows. And we call this a structure, and the relationship of behavior. For the purpose of this talk, I'm going to be calling these node concepts and relationship edges. And you'll see why in a sec. So through these models, you can kind of see the changes that occur. And that's really the idea here, is we want students to be able to represent their understanding in ways that are not linear and show the complexity of the learning process. And that requires that we come up with some way to measure what it means to restructure your knowledge. And this is where some network approaches come in. So luckily, there have been huge advances in the last 30 years around how we understand network graphs. And what I'm trying to do is see how those approaches fit in the way that we assess our student learning for topics like biology and statistics, very domain-specific topics. Okay, so why do we study concept models? Well, what's great about this is there's some real benefits because it allows people to represent their knowledge. And even if you have a few terms, nobody is going to create the exact same model. Everybody has a unique representation. It's kind of like a snowflake, right? It forms through crystallization, and you get these different structures. And so by thinking about how those structures are different, we can say, oh, these are a proxy for the measurements of their cognitive structure, and everybody has a unique one. And even if I give you the same list of terms, you're going to come up with something different. What's also nice about this concept model idea is that we can scale it. So we can combine models together to show aggregate ideas. So really the purpose of this project is kind of twofold. I want to use these network analysis approaches to analyze student changes in their models to show as evidence of learning, but then also there's some deeper questions about what do these changes mean about the process of learning. And eventually I want to be able to simulate the growth of these networks and compare different simulations to what we see in the real world, in the classroom dynamics. Okay, so that's what I'm going to share with you today, is kind of how we've progressed so far. So I'm going to talk about one data set in particular, but we actually have two. And I'll be focusing on some of the latest data from the University of Washington. So this is collected from statistics courses. I have over 185 models, and students are asked to make these to explain how concepts are related throughout the quarter. And meanwhile, my colleagues back at Michigan State, who I'm still working with, they have over 13,000 models. So their set is a lot bigger. And they're explaining things like, create a model to explain how genetic variation can lead to phenotypic differences. So what's nice about this is we're already starting to bridge across disciplines and thinking about how this educational assessment approach can be used. Now, what I'm going to share today is a very limited data set, so I don't want you to take away too many big generalizable inferences. Obviously, we're going to have to do a lot more to make these patterns more salient and see how reproducible they are. But there should be 3 time points: beginning of the quarter, middle of the quarter, and end of the quarter. And I have 2 sections. So one is winter 2020 and the winter 2021. And of course, winter 2020 got a little interrupted at the end. We ended up having to shift to online in the last few weeks of the quarter. But for the most part, we were in class. Meanwhile, winter 2021 was all distance learning and very disruptive because of the pandemic. So altogether, the data set I'm going to show is of 67 students, 185 models, and this all was, I sent the proposal to the IRB to get approved. All right, so here is kind of the methods. First, of course, we assess the students, so I'm giving them these tasks. They take pictures, they usually hand draw these. I'll show you an example of that. And then what we have to do is digitize them, so we transcribe them to a format called CMAT. And from this, we do a lot of pre-processing and combining so that we can put everything in a consistent format, fix any misspellings that the students might have, and eventually what we do is transform these into graphs so that they're networks. And the last step, of course, is combining those into aggregates. So here's what a typical concept model would look like. So this is week 2, very early in the quarter. Again, this is statistics. I give them a list of terms, a really long list, so they're not all depicted here. And they're asked to show how these are related to explain, how statistics works. So as you can see, some of the terms like data come up, and descriptive statistics, you see things like numerical, categorical, those are labels for different types of data. And this is a fairly robust network for somebody just starting. And then of course we digitize these. So this is the CMAP version. And as you can see, it's already starting to look more like something a computer could analyze. And then by week 10, they create these kind of final models. And this is similar to what you might say a concept map, but models tend to be more purposeful. So you can see a lot more connections, a lot more relationships. They've added a ton to their original model and rewired a lot of this. And again, this is meant to be kind of a proxy for what we think is happening in their head, what's happening to their cognitive structures and how they relate ideas. And again, here's the kind of digitized version of that. Now, what's great about this is as an instructor, I can see the changes that they've made. I can look at different ideas and say, hey, I think you need to spend more time reviewing this concept. So it's great for my formative assessment. And of course, the last one is a summative assessment. And students can kind of continue to use this. I use a lot of portfolios, so they can reflect back on how their understanding has shifted throughout the course. So how do we do this? So once we have the students transcribe models, we have to turn them into a network graph. And these are ways that we can study the semantic structure. So if we had an original concept map like this, it would eventually get turned into something a little more simplified, like these ones shown here. So this is the same three models, except I've kind of stripped away all the labels and just showed how the concepts fit together. And you can see the growth that's happening and how early on a lot of ideas were all connected, and now they're kind of starting to differentiate. You're starting to see a spread out of ideas and more nuanced connections. So this is just one student. Well, what happens if we wanted to combine multiple students? So the nice thing about these network graphs is they're scalable. I can combine the class as a whole to show how students have brought these ideas together. And what I'm going to show you now is the results of where we're at right now. So the first one is, students add more ideas and relationships as they learn. That was already pretty evident in that example I showed you. The class as a whole shows some concepts becoming more centered and connected into higher centrality, higher strength between the connections. And then I'm also going to show you that there was district growth between these corridors. So here's an example of a graph. So I've got box plots here. Let's focus on the left side. So over here we have 3 time points: week 2, week 3, and week 2, week 4, and week 10. And you can see the number of nodes is displayed here for each of the graphs in this data set. And this is only the 2020 data. And as you can see, as the quarter progresses, students gain a lot more concept models, or gain a lot more concepts into their model. And this is paralleled with increased relationships. So you can see they more than doubled the number of relationships, the connections they're making between concept models. So this is great. This is still kind of a linear scale, but it gives some evidence that there is this kind of aggregation of knowledge that is happening. So what about the whole class? So again, I mentioned that you can take these models and combine them. So let's look at the largest component of the combined models. So here, each of these dots represents a concept. The lines represent the relationship between concepts. And as you can see, the one in the middle is data. So it's labeled right at the center. And these concentric circles show kind of the distance away from the center. And again, this shows how much strength each of the nodes has. So the closer it is, the more center and the more connected it is. So here's at week 4. Again, we're starting to see some ideas being brought more into the periphery, from the periphery into the center. We also see additional ideas on the outside. And when we get to the week 10, a ton more ideas, everything's kind of moving into the center. And of course, you can see a lot more connections spread out throughout the whole graph. So we can see the progress of the class as a whole for the 2020. And this is really great as an instructor because it makes me think, oh, I help my students kind of develop a stronger cognitive structure so that they can navigate these complex ideas within the classroom. But when I repeat this for 2021, we see growth is noticeably different. And at least visually, we see fewer concepts along the periphery at the final state, right? There are fewer kind of extra ideas out here. And then the ones in the center are just kind of pushed out a little bit more. So these are the questions I have now is how do I understand this? How can I turn this into some kind of report that an instructor could understand that maybe isn't familiar with network analysis? And if we do a side-by-side comparison, you can really see there was some visible differences here. Again, the 2020, almost all in person except the last few weeks, whereas the 2021, very disruptive, trying to teach statistics online without a computer lab. And if we try to look at the concept models and the relationships, again, try and turn it into this linear one, these dark bars are the first data set I showed you, the 2020, and then the 2021 is the second one. And I haven't run the statistics on this yet, but it's probably approaching significance here by week 10 that there are fewer concepts and fewer relationships. So disrupted quarter seems to be reflected in the cognitive structures. And more importantly, though, I want to move forward in thinking about how these networks can be used as evidence of learning. And a lot of previous research, especially done in the 90s, was focused on what it means to be an expert and develop expertise. And one of the big studies, one of the big findings from all of that research was that experts have a really effective cognitive structure, and that's what allows them to do memory retrieval process through chunking and pattern recognition. So the idea is that if we focus on developing students' cognitive structures, and that will help them develop expertise and become more expert-like in their performance. Now, the big highlight of this project, and again, we're kind of still in the early phases, is trying to connect the learning process to learning analytics. A lot of learning analytics is all about behaviors of students, and what we want to do is try and bring in some more of that learning theory that makes the education perspective so valuable. We also want to connect the practices like modeling to STEM education. And again, this is an opportunity to bring in network analysis into the classroom, an area that hasn't really been applied very frequently. And for next steps, luckily we're already on the way. We were awarded an NSF grant at UW to use the HIKE clusters. So these are supercomputers. And this is great for this project because if we want to run these models to kind of simulate network growth, we're going to require a lot more computational power. So that's the next step for us and already moving forward. And we'll be seeking more funding as this network grows and we get to find more partners. So I'd like to acknowledge the SRCP seed grant that provided by the Office of Sponsored Research. Thank you so much for doing that. It's really helped me take this idea and turn it into something that I can kind of point to and say, this is what my ideas are looking like. And now I have some evidence I can share with you all. I'd really like to thank Prim and Darcy, two of my students who are now undergraduate researchers. They've been working on this project for over a year. This work would not have gotten done without them. And our newest member of the team, Scott, who will be trying to do some handwriting recognition to kind of help ease that transition from the written models into digitized models. And of course, my colleagues at Michigan State, Tammy Long and Jolene, and a lot of the work I've done is inspired by early work by Joe Dower and Dr. Eifenthaler. So thank you all for attending, and I'd be happy to take questions. I used a lot of noun project images, and then here are my references. I'm happy to send this slideshow on request too. All right, thank you.
Great. Thank you so much. At this point, if you've got questions, you can either use the raise your hand icon or unmute yourself and ask a question, or even pop it in the chat if you'd rather. So I have one. In your description, you mentioned that experts have a very highly networked model, which allows them to retrieve content. What I'm wondering about is how you deal with misconceptions that are actually, they can build and build into a networked model until it
Yeah.
reaches a point where it doesn't work anymore.
Yeah, that's a great point. So I'll kind of answer that in two different ways. First is I don't think we're actually completely sure how these networks are supposed to grow. I've seen kind of three different ways, kind of hypotheses, right, of how these things should grow. Some view it as kind of a tree branching, like as you get more concepts, you see more of subsets of ideas, and those become kind of more nuanced, and the branching should happen. Another model is kind of like what we call pruning occurs. So you gather ideas, but then not all of those ideas stick, and you start to see solidification of a structure, and it becomes more what we call parsimonious, like fewer pathways, and everything kind of comes more connected to a few big ideas. And then you also see things like preferential attachment, where once you have an idea, everything kind of connects to that idea. So we're not exactly sure how these models will grow in the classroom, and I think that's why this work is so important. But to address the misconceptions idea, yes, without an instructor kind of leading you away and actually looking at your model, it can go quite astray. We know that there's a conceptual change theory, and there's ideas that once somebody has kind of a misconception, you really have to provide them evidence that can't be explained with their current cognitive structure, and it puts them in discomfort, I guess you might call it. I'm forgetting the word right now.
Cognitive dissonance.
Cognitive dissonance, yeah. So once you put somebody in cognitive dissonance, you also have to provide them a better explanation, one that's more feasible and attainable before they kind of switch over. So there's literature on that. There people do study that, and I think it'd be interesting to see how we could track misconceptions through something like this. And I know in biology, there's some work on evolution that's looked at that, where they can see how canonically scientific ideas increase, and the misconceptions decrease over time. But for this work, I'm not so interested in evaluating the correctness of ideas. Joe Dower, the previous postdoc who worked on this, he has done a lot with that. But to me, it's much more interesting just that we have so many new ideas that we're bringing together, and it's kind of in my philosophy that things will work out, and sometimes things that people deem as misconceptions actually become revolutions in science too.
Thank you. Marie Blakey, you have your hand raised.
I do. As I was listening to, I was thinking about our focus on high impact practices, right? And your desire to see if you can take your results and make them something that would be helpful to other instructors. And so I was just wondering if you could reflect a little bit about the implications of your research, because I kept thinking, wow, I wonder how the pedagogy in the classroom also affects the network of ideas and the relationships of ideas, when you do teamwork, right, which is sort of a human relationship that affects it. So I'm just wondering if you could talk a little bit about how this information possibly could help instructors, but maybe that's another whole area of research and you need 10 more years.
Yeah, absolutely. I think there's a lot of different directions this could go. And, of course, anytime you're designing like lessons, it's all about what goals you have for your students, right? And so, for some people, it's fine if your goal is you want students to be able to perform a statistical test on the final exam, right? And do it all by hand. An instructor who is effective is one that gets their students to meet their goals. And so for me, I'm more interested in helping students pick the right kind of statistical test because they understand what kind of data they're working with. And so to me, it's a lot more about, connections and thinking about how these ideas relate rather than, actually doing the writing out all of the transformations that they need to do. So I think it does come down to goals. I think what's really interesting about this is it's starting to take assessment and think about it in a way that cuts between the individual, a group, a whole class, or whole cohorts of class. So whenever you're working in a group, of course, the important thing is that you don't think the same, that you have different perspectives, you have different thoughts about how the world works, and you have different mental models. So if we can get teams to work together and create kind of a consensus model, and there are researchers who study this stuff, maybe we can think about where the overlaps are and what the consensus parts are, and then also identify, well, here's where we think about things differently. So by creating these kind of boundaries around the sets of networks, we can start to do comparisons, and add things together, subtract things out, and of course, like I said, most interested in look at how things are changing over time. So yeah, I think the implications are that, it forces us to think about what are the goals of our teaching and how does that relate to what, again, aligns with learning theory of cognitive restructuring, and how can we create assessments that are scalable and help us understand where the classes as a whole versus groups versus individuals.
Sarah.
Thank you so much, first of all, for presenting. So my question was, and I was doing some stuff behind the scenes, so clarify for me. So this is an option to assess students in replacement of essays, like for exams or things like that. Like this could be a possible tool.
Yeah, I would consider it a supplement, right? Like it's not an essay, and it's not going to show you the same things that
right.
building a model of a
another
cell
tool,
would, right?
Another tool, right? Yeah. I love this idea. I was curious if you found that students, my family is an English second language family. I'm curious, did you find that during the assessment that it was more accessible to students?
Yeah, so I think, I've had a lot of success with it, I feel like, in my class, but and I know there is some research on it. I'd have to track down the source. I'd look for that. But I have heard that these are, especially for second language learners, ESL, they help to create a structure so that, the distracting things about grammar are now a little more simplified, right? And so, yeah, it provides kind of a portal into how you're thinking about these ideas that, doesn't require you to have mastery of written language. But again, I think what I'd like to think of it as, it's another tool in this toolkit that instructors have to assess their students, right? I also use a lot of in that quarter, I do weekly journals where students write out, a prompt about what were their struggles through the week. And to me, that gives me the more insights than any kind of assessment or quiz that I give them, because I can really get a sense of what they're stuck on. So yeah, I think there is a lot of potential for exploring how this helps kind of level the playing field with the language background.
Natalia.
I'm wondering, so I love the integration of networked learning into your approach, but if I was an instructor watching this, I might say, this seems like so much work, I can't do this. So how much more work is it to introduce these different kinds of assignments into your teaching practice, and then to assess them? Then, obviously it's a lot more work than scoring a multiple choice quiz that can be maybe automated, but can you give us a sense of just how much more time and effort it takes to do this? And especially for your colleagues at Michigan State who are working with sample sizes that are, exponentially larger, how do they do it?
So I think, I think you can slice this different ways. And again, it depends on what your purpose is as an instructor, right? Maybe this is just kind of the pre-post I want to see what's changed about your knowledge. I also use a lot of other reports and things like that as the main assessments. So what I like to do for this one, though, is I have a rubric that focuses on kind of, I think it's like 4 areas. Like, do they have concepts that make sense? Are the relationships clear? And then we call it a proposition when it goes from concept to relationship concept. If you were to read that, looking across, does that statement make sense? Is that a proposition that holds weight, or is it nonsensical? So that's another area. And then, the last one is kind of overall, does this explain what the prompt is supposed to do? So having rubrics, I think, is a really quick way to kind of speed things up. At Michigan State, where we have 400 students,
Right.
they leverage the learning assistants. And the nice thing about that is, you can tell the learning assistants, hey, I'm looking for these ideas being connected. And it starts to boil it down a little more, so that instead of LAs looking at essays, which of course is really difficult to get calibration on, now they can look at specific propositions and be like, okay, here, everybody, tell me which of these that the students have. So it depends on your goals. I think I use a lot of it for more of a formative style, where it gives me feedback. I can see where students are. But yes, the part of aggregating the models, that is not easy to do right now. And even though we have kind of the individual ones, it's still really hard to go from that, digitize it, and then get a class report of like, here's how everybody did on that assessment. I'm only doing this stuff after 2 years from the time I first gave out those assessments in winter 2020. So it takes time.
Thank you so much, Dr. Trujillo, for your talk and for fielding all the questions. Anybody who has questions for him can certainly reach out via email. And I
Here, I'll
encourage.
put my email in the chat for you. Thank you.
Wonderful.
Great sharing.